Let's have your hands and eyes at the smartboard. You should already have your guided notes passed out and have those in front of you, something to write with. We're going to be discussing scientific inquiry today, and I know that a lot of what we're going to be discussing, we probably already discussed in class as we've done our hands-on activities, but this is going to help people who need to see it in writing, who learn better that way. It's also going to help you next week when you're going to design your own experiment, that you have something that you can look back at in case that you forget, what is she talking about? There's some notes that you can refer to. So what is scientific inquiry? Scientific inquiry refers to the diverse ways in which scientists study the natural world, and they propose explanations based on the evidence they gather. Okay, so the scientific process is something that you might think of as just the scientific method, and you've heard of the scientific method before, but the scientific process is different than the scientific method because scientific process is not as rigid as this step and this step and this step as the scientific method leads you to believe how scientists really work. In the scientific process, there are guidelines that you go through, but it's very fluid and it's always moving. It's not as rigid as the scientific method leads you to believe. So kind of tweak your thinking about that just a little bit, and then if you would keep it in your thoughts that we use the scientific process rather than the scientific method, that's going to be more accurate. So the first thing the scientists typically start with is to pose a question. And scientific inquiry often begins with a problem or a question about an observation. And questions often arise from experiences or observations. These questions must be able to be answered by making observations and gathering evidence. So making observations and gathering evidence. Scientific inquiry cannot answer questions about personal tastes or judgments. Okay, so an example question would be, does the mass of a paper airplane affect the distance that plane can fly? Okay, so that's something that you could test. You could build different airplanes with different types of materials that might have different masses, and then fly them to see if the different masses affect the distance that the plane can fly. That's testable. A scientific or a question that's not scientific would be, what's on my iPod's playlist? So that's not something that you can test. That's based on somebody's personal taste. So write SQ for scientific question, draw a circle and a little line through it so you know this is not a scientific question. Like, what's on my iPod's playlist? That's just a question. That's not what would be considered a scientific question. Okay, so after you pose a question, then you're probably going to want to start researching background information. And you want to research information that may be important to understand the problem. This could be information already known from a past experience or observation. So when we did our M&M step-by-step lab, we were researching background information for the experiments that you're going to be doing next week. You have a past experience and you made some observations, and you'll be able to use those in the future. And scientists usually have to research in those ways in order to develop an educated hypothesis. So scientists may need to research in order to develop an educated hypothesis. So after you've done background information, then you're going to want to start developing your hypothesis. And a hypothesis is a possible explanation for a set of observations. A hypothesis is not a fact. It's not a wild guess, but it is one possible way to explain a group of observations, and your hypothesis must be testable. So your hypothesis must be testable. Researchers must be able to carry out investigations and gather evidence that will either support or not support the hypothesis. So researchers must be able to carry out investigations and gather evidence that will either support or not support the hypothesis. And the hypothesis should be written in an if-then format, and we discussed that a little bit yesterday. That there are two parts to your hypothesis. You don't have to say if or then necessarily, but you need to make sure that you have, if this happens, if this is something that occurs, then this is going to be the result. This is what you think will be the result. So if we use the example question, does the mass of a paper airplane affect the distance the plane can fly? An example hypothesis might be the researcher believes that the paper airplane with the most mass will travel the farthest distance. Okay, so the researcher believes that the paper airplane with the most mass will travel the farthest distance. So the if part, B, if you made airplanes with different masses and you're going to pick one, you think that the airplane with the most mass, okay, then the then part is that will travel the farthest distance. So there's two parts to this. Okay, you know that you have to have a paper airplane and you have to pick whatever mass that you're going to pick. Maybe it's the least mass, maybe it's the most mass, but you have to pick something. Then what will happen to it? Well, it'll travel the farthest distance, or maybe it will travel not very far at all. Okay, the least amount of distance. So it has two parts. And once you have designed your hypothesis, then you can start designing your experiment, starting with talking about your variables and controlling your variables. See, a variable is a factor that can change in an experiment. And in order to maintain a controlled experiment, only one variable should be changed at a time. The manipulated variable or it could be called the independent variable, is the one variable that's changed on purpose. And as seventh graders, you're master manipulators, I'm sure, with your mom and dad. You know what to say and how to say it to get what you want. And I'm sure that a lot of what you're doing is on purpose, and that's manipulation. So you know that the manipulated variable is the variable that you're changing on purpose. The other variable is called the responding variable. Now, the responding variable or the dependent variable is a variable that changes in response to the manipulated variable. Okay, so the responding variable is dependent. Like you're dependent on your parents, you rely on them. This responding variable relies on the manipulated variable. If you didn't change anything on purpose, then you wouldn't have a responding variable. Nothing would happen. But because you have a manipulated variable, whatever happens in response to that, that's what is the actual responding variable. Okay, so let's say for our gummy bears, okay, if we tested different color gummy bears, the manipulated variable would be different colors of gummy bears. Okay, and we put those different colors of gummy bears, one in each cup with the same amount of water in each cup, and you wanted to see which color of gummy bear was going to dissolve the quickest. Well, then your responding variable, okay, this is your manipulated, the different colors, the responding variable would be the amount, AMT, that period, that's the abbreviation for amount, AMT, amount of time to dissolve. Okay, so the amount of time to dissolve, that would be the responding variable. Now, an experiment where only one variable is changed at a time is called a controlled experiment. And all experiments should aim to be a controlled experiment, because it's easier to determine that the result is directly related to what was changed. Okay, so it's easier to determine that the result is directly related to what was changed. If you change 3 things in an experiment, then you're not sure if the result is because of the first thing, second thing, or the third thing that you changed. And that's not a good experiment. So if you change one thing, that whatever happens is because of that one thing that you had changed. We also need to discuss forming operational definitions. And an operational definition is a statement that describes how to measure a particular variable or define a particular term. So for example, how would you know when the researcher considered the M&M to be dissolved? Would you wait until there's no longer anything in the water except for maybe a chocolatey color? Or would you wait until maybe the outer shell is dissolved? You need to set your operational definitions so you know, and everyone who tries to replicate your experiment knows what the data is kind of coming from, what perspective the data is coming from. Because if Mrs. McDaniel's class tried to do the same experiment and you haven't set this operational definition, they might take data based on waiting until it completely dissolves and nothing's there except for chocolatey water. Whereas our class might have only waited until maybe the outer shell has dissolved. And so our data would be skewed because we didn't share that same operational definition. So once you have all of those things set, your variables, your operational definition, then you need to start thinking about your procedures. And your procedures, that's a step-by-step description of exactly how the experiment will be performed. Now, your steps must be numbered or bullet pointed, and in a logical order of how it's going to be done. Now, these procedures should also include many details. So another researcher could replicate your procedures exactly. Now, replicating an experiment reduces bias, which means that there will be less of a chance that the results could be influenced by opinion or human error. And the procedure should detail the number of trials necessary. Number of trials necessary. The researcher should try to conduct at least 3 to 5 trials to reduce bias and human error. Now that's probably a good number for 7th grade, but know that scientists do thousands upon thousands of trials. So 3 to 5 in the real world would not be very many, but in 7th grade that would be okay. When you collect data, you want to create a table to collect and record your observations. Data tables should have a title, a place for all trials that you're going to conduct, place for the average, and include units of measure. So not just the numbers, but also your units of measure, which is what I encouraged you to do in your gummy bear lab. You'll also have to interpret your data and graphs. There's different types of graphs that you might use. So you might use a bar graph, and this is used to compare data. And it helps us to see similarities and differences. So an example of a title might be a comparison of brands of popcorn. Okay. And there's also a line graph. And this shows the relationships between two variables or sets of data. This shows how one variable is affected by the other as that variable is increased or decreased. And it helps to show trends and make predictions. So an example might be the relationship between mass and speed. Now, when you talk about all graphs, to recall which data goes on which axis, when you're making a graph, you want to use this mnemonic device, dry mix. Okay, so D for, and the dry stands for dependent, like the dependent variable, which we also know is the responding variable. So there's two different names for that, dependent or responding, and that's on the y-axis. So your dependent variable or your responding variable, that's the same thing, is always labeled on your y-axis. Okay, let's talk about mix. That's your M for manipulated, I for independent, and X for x-axis. So we know that the manipulated variable or independent variable is shown on the x-axis. Okay, so how do you know what's what? Okay, so draw like a little graph. We know that x to the left, okay, x goes right to left or left to right, but y is to the sky. Okay, x to the left, y to the sky. And if you remember dry mix, then you'll know that the dependent variable or the responding variable goes on the y-axis, that's up and down, y to the sky, and the manipulated or the independent variable is going to be labeled along the x-axis. Okay. Now, to recall all required parts of a graph, when you're making a graph, you want to use the mnemonic device TAIL. Okay, TAIL, the T stands for title. Every graph or chart should use a title. You need to have the axis or the axes labeled. So you want to use dry mix to remember that. Okay. I is for interval. So when you're making your graph, those spaces should be constant and start at a 0. And L is for label. So include your labels and your units of measure. Okay. Now, scientists also need to draw conclusions. So a summary of what was learned from an experiment is a conclusion. It's a summary of what was learned from an experiment. So does the data support the hypothesis? That's going to be what's included in your conclusion statement. Did you collect enough data to be able to tell those things? And did you identify anything that may have affected the results of the experiment? So anything that might affect the results of the experiment, you discuss that in your conclusion statement. Now, conclusions often lead to new experiments. So for example, when we did our gummy bear experiment, it didn't turn out like we thought it would, but it led you to start thinking about other experiments that you could conduct based on the observations that we made from that experience. So scientific inquiry is a process with many paths, and know that there is not one set path. And once you've completed your research and you have drawn your conclusions, it's very important that you communicate your results. So when scientists communicate their research, they describe their procedures in full detail so that others can repeat their experiments. The scientists must be able to communicate their experimental findings through writing and speaking to make a difference. Because if you cure cancer, but you can't communicate how you did it, either in writing or speaking, then it didn't do you much good. So That completes our notes for scientific inquiry. You can put your guided notes in your classroom folder, and we'll continue with our experimentation next week. Have a good weekend, and make sure that you are well behaved for our guest teacher.